talking about solids, and so we're going to talk about a technique used to investigate solids called X-Ray Crystallography. So here we have photographs of some beautiful crystals. This is a mineral, and this is a snowflake. Crystalline solids, you'll remember, have long-range patterns in how their atoms or molecules are arranged. They can make these beautiful geometric shapes. A snowflake forms that way because of how water molecules arrange themselves when they solidify. You don't do this on purpose, right? This crystal here formed, probably took a while, but nobody made that. You don't get out a laser or anything and cut it like that. It has to do with how the ions arrange themselves. So how do you figure out how the arrangement, how the atoms are arranged? You can use X-rays. So remembering that waves can have constructive interference, where they line up together and the amplitude is increased, or they can have destructive interference, where they line up exactly opposite, trough to peak, and they cancel each other out. Remember the guy with the box on the beach? Double slit experiment, right? And the sunlight coming through had constructive and destructive interference and produced that fringing in the bottom of the box. That can happen with any electromagnetic radiation, not just visible light. So you can also do it with X-rays. So the light passing through two slits separated by a distance that's similar to the wavelength. So the distance of the slits and the wavelength of the radiation are significant, but you can get an interference pattern. Doing this with X-rays, we can investigate the structure of crystals, because the distances between atoms and molecules in the crystals is similar to the wavelength of X-rays. So you can take a beam of X-rays and shine it on a crystalline solid, and using an X-ray detector instead of the bottom of a box, right, you can look at interference patterns caused by the X-rays going through the crystalline solid. So the spacings between those atoms are in the order of 100 picometers, which is in the X-ray region. So how does this work? If we have X-rays coming in from the same source, they will be in phase with each other. As they hit this solid, they are going to reflect off of different planes of atoms in that solid. So when this one reflects off, it travels a certain distance. Ray 2, because it went into the interior of the solid and is reflected off, travels a longer distance. Does that make sense? And so geometry tells us what that path difference is. The difference in path is equal to 2 times A, where A represents the separation between those two planes. What we do is we shine the X-rays at an angle theta relative to the surface. You'll see interference, constructive interference, if the difference in path length here, 2A, is equal to some integer times the wavelength. If it's 1.5 times the wavelength, then you'll get destructive interference. If it's somewhere in between, you'll get varying amounts of interference. So we can vary the wavelength, vary the angle here until we get constructive interference. And then we can use this equation, sine theta equals A over D, to find out what the spacing is. So D is, where did D go? I'm blanking. Where did the D come from? Oh, there it is, right here. Duh. So D is, I'm sorry, backing up here. A is not the distance between the layers. D is the distance between the layers. The difference in distance traveled is A and A. Sorry, I screwed that one up real well. So the sine of theta equals A over D. A being this little distance here, and D being the separation. So we can find out what A equals. A equals D times sine of theta. That's all just geometry. And then we can plug D sine theta in for A here, and this integer n times the lambda, the wavelength of the X-rays, is equal to 2D sine theta. This is called Bragg's law. Most of these things are named after the scientists who observed them. You do not need to know how to derive Bragg's law, okay? So don't worry about that. You should know how to use Bragg's law, though. For the exam covering this material, I will give you a bunch of equations. So I would give you n lambda equals 2d sine theta. There's not going to be any information about what is d, what is theta, what does it mean, okay? So you need to know how to use the equation. And we're not going to do tons of calculations with this. But we want to have an idea of how this works. Any questions so far? So here is a photograph of an early X-ray. Well, I don't know what you would call that, actually. Crystallograph? I don't know. The results of an early X-ray crystallography experiment. So you vary the angle theta until you get constructive interference. And then you can calculate the distance between the layers as n lambda over 2 sine of theta. X-ray crystallography is used and has been used to identify the structures of lots of different things. Probably the most famous one is the double helix structure of DNA. Watson and Crick used information from X-ray crystallography to help them figure out the structure of DNA. It can be used on proteins, simple atomic lattices, ionic compounds, all sorts of things, enzyme proteins, all sorts of things to figure out the structure of those molecules. So let's do an example problem. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. Well, this is going to require Bragg's law. You have kind of a clue up here because the example's titled using Bragg's law. Those sorts of titles don't show up on the on an exam. So the rearranged form was d equals n lambda over 2 sine of theta. Oh, but that's not what I'm trying to calculate. That would be for calculating d. So the rearranged, the regular form of Bragg's law is 2d sine theta. N lambda equals 2d sine theta. So we're going to need one of those, right? So we're given some numbers here. We need to identify these. The spacing between layers, what variable was that? D. So this is D. And then we're supposed to calculate the angle. So we're looking for theta. And 154 picometer X-rays. What's this number representing? Lambda. That's the wavelength of the X-rays. And then we're told to calculate this for n equals 1. So we're trying to find theta. Well, we could find sine of theta fairly easily by rearranging that equation. I'll do it down here. So the sine of theta is going to equal n lambda over 2 times d. We do that just by dividing both sides by 2d. Those cancel out. Sine is a function. You can't divide by a function. You have to do the inverse function. The inverse function of sine is inverse sine. And you have a button on your calculator that'll do that. It's the s to the minus 1. So let's go ahead and calculate what sine of theta is, and then we'll find out what theta is. So we're going to plug these numbers in. N is 1, just an integer, no unit. Lambda is 154 picometers. And we're going to divide by 2 times the distance between layers, 157 picometers. It is very important to put the units in your equations. So when we look at this equation here, we see that we have picometers in the numerator, picometers in the denominator. The units cancel out. So here it's not mattering what unit we use for the length and the wavelength, as long as they're the same unit so that they can cancel out. You can't have centimeters and meters or something with picometers. So that's going to give us a number, 154 divided by 2 divided by 157. 0.49 0.446. Those are whole numbers for the distance and the wavelength, but those are measured values, and so they only have 3 significant figures. So this value has 3 significant figures. Don't round it yet. It's tempting to just say 0.49, but keep some extra digits. Now, to find what theta is, theta will be the inverse sine of that number. Make sure that your calculator is set to degrees and not radians. I did this on Thursday. I don't know how my calculator got set to radians. I never use radians. But there it was, and I got the answer wrong. So the sine and inverse sine should be close to the sine button on your calculator. And so I'm getting 29.36989. This would be degrees because I'm using my calculator in degrees mode. If you had it set in radians, then it would be in radians instead of degrees. I won't trick you with sig figs on something like this, but 3 sig figs here, 3 here. It would be reasonable to round this to 29.4 degrees as theta. Sig figs are not the best thing to use when you're doing sines and inverse sines, but that's all that we've learned, and so we're just trying to be reasonable. Any questions?